do this. All right. Longest nice subarray. You're given an array of positive integers. We have a subarray nice. We call subarray nice if the bitwise and of every pair of elements that are in different positions in the subarray are equal to 0. Every pair of elements in different positions. Every pair. Return the length of the longest nice subarray. The bitwise and of every pair. Okay. A subarray is a contiguous part of the array, so it has to be all connected. I see. So the longest nice subarray here is 3, 8, and 48. Because 3 and 8 is 0, 3 bitwise 3. So for bitwise stuff, so if you look at 3, you're looking at the actual bits in binary to do the AND for. Wise AND does AND operation on every binary bit within numbers. So, for example, if you have 3 and 8, a bitwise AND of 3 and 8 is going to be in binary. 3 is going to be like 1, 1. This is in binary. 3 is going to be 1, 1. 8 is going to be 1, 0, 0. Like if you think about binary, arithmetic, the first, the leftmost, rightmost digit bit is 1s, then powers of 2, or equal to the value of the rightmost digit is 1, and then the next one is 2, and then the next one is 4, and the next one's 8. Just like place value in decimals is going to be like 0, 10, 100, 1,000, increasing in powers of 10 for decimal and 2 for binary. So here, just to make it the same bit length, 1, the rightmost 1 ANDs with the rightmost 0, and that becomes 0. The second rightmost 1 ANDs with 0, that becomes 0. 0 and 0 is 0 for the third bit, and then the fourth bit is 0 and 1. And that becomes, that's also 0. Okay. So, what we would need to do here, because it's a subarray, I'm thinking it's probably sliding window. And for each element, so so you increase the window on the right, and then increase the element on the right, and then you close the window on the left. Is that correct? Increase the window on the right, so you take in more bits up into, you take in one additional bit, or you take in a number in all its bits on the right side, and then you determine how far left it could be. And when you determine how far left you can be, you close the window down, removing bits until you have something that doesn't have any overlap. Basically, if there's a bit in the same location within all the numbers of the window, then the bitwise AND will be something besides 0. If you do, yeah, because every pair of elements needs to be different in terms of its bits. Like 48 would be in binary, that would be 132, 06, no, 132, 116, 08, 04, 02, 01. So 48 has 1s followed by 4 zeros, so there's no overlap. So if there's ever another number that has any bits in the same that are kind of on anywhere else within the subarray, then that just is not gonna. That's gonna be a pair that has non-zero and. So yeah. So here we sliding window technique. We're going to add numbers and their corresponding bits. Which is going to be for each loop. Extend right index, add value, or add bits of number at right index. And then close while left number has any overlap with the right number. Because you're always adding it. You're always adding so that it's the only thing that you can possibly have issues with is the rightmost number. So while the left number has any overlap with the new right number, remove left, and then compare window size, which is the length of subarray, to current best. Okay, so let's say answer is 0, n is the length of nums. For every right index in the range of n, the right r num is going to be equal to the nums at the right index. And then we're going to add bits. So we would need to determine which bits are in the right side, I believe. Is that necessary? I'll say left is equal to 0. Right. Yes, I don't really need to know. I don't think I need to know what bits are in the right, as long as the left doesn't match it. So So I think it's just while left doesn't equal right, while left is less than right, and the bitwise and of let's say the left number, which is going to be nums at left, and with the right number doesn't equal 0, then we're going to remove the left side. So left plus equals 1. And then the answer is going to be the maximum of the current value of so window, the size of the window is going to be equal to the right minus the left plus 1. And then the answer equals max of answer and that size. Turn answer. I think all you need to worry about is adding. So if our invariant, if we know what's true is like the window is not overlapping, anything inside the window is not overlapping, the right side could add stuff that overlaps. That's not right. Let's say you have two duplicate numbers. You need to collapse it all the way. Yeah, you need to collapse it all the way. How do you... So let's say you had 1 0 0, 1 0 0, 0 1 0 0. Like these are the bitwise representation of the bit representation of the numbers in the array. And then you had a 0 0 0 1 0 and a 0 0 0 1 0 0. So if you do just a bitwise AND between the first and last, you think that everything's fine. It's not fine because you have a matching. So I think you do so if you did a bitwise, what if you did a bitwise exclusive? If you did a bitwise OR, if you did a bitwise OR of everything in your window, and then you did a bitwise AND of that. If you did bitwise OR of everything in your window, then your window would look like 1 1 1 0 and then 0 1 1. And if you did a bitwise AND between that and between the bitwise OR of your window and the bitwise AND, that would be non-zero. And if it's non-zero, then you know that there's some overlap and you need to remove that overlap. You need to remove that overlap, but then how do you know when you have removed that overlap? Okay. How do you know when you've moved that up? I think maybe you maybe if you take out, like, the, in theory you could do a count of the bits. I'm not sure if that's efficient enough. Like if you do a count of the bits, like there's one, like just a counter, like the 0-bit spot, 1-bit spot, 2-bit spot, 3-bit spot, and you just kept track of that. And then whenever you see a new number, like this is the first 3 numbers, if you see a new number and the counter for a particular index in the bit is bigger than 1, then you need to go down below that. You could do that, and then you'd be able to tell exactly when it actually went down to 0. How big are these things? 10 to the 5th. And each number has, so each number is 10 to the 9th, which is a million. If you go in million in terms of bits, I think that's roughly 32 bits. So all 32 bits are in play. All right. All right. Fine. All right. I'm just gonna do the brain dead way and then see if I can optimize it. So, the brain dead way would be, let's go ahead and have a compare counter, or compare some array of comparisons, some array of powers of 2 that basically has a 1 in each bit. So powers is equal to 2 to the power of n, or k, for k in range of I think 32. And let's go ahead and just print. So if you have this array, then you can compare with these powers using bitwise OR to see if there's a certain bit that's on. I think there might be other ways of doing this, but this is fine. So each number bit counts is going to be 0 times 32. So if we take that right number and then we just add it to our bit counts. So for each p in powers, bit value for that particular power is going to be p bitwise or bitwise and with that right number. So this will return 1. So like powers would be like first power 2, second power 2, third power 2, like 1, 2, 4. And as you increase it and you're taking bitwise and of that in the number, it basically is 1 if that value in that number is 1. So the bit value is that, and if the bit value, I don't know if you need a bit if statement here, usage bit counts of this index. Okay, I need the index here. Say p index is every in the range of 32. And the power itself is going to be powers at this index. Taking it bitwise and the bit counts for this pindex is going to be, well, it's going to add equal to the bit value. Now, so if it's 0, then it increments by 0. If it's 1, increments it by 1. So and then I'm going to do a quick set here. So if it has more than 1 for it, can it possibly be bigger than 1 or bigger than like 3? No, right? Because there's at most everything before that has to be unique within the window. So you can't actually exceed 2 once you add in this bit. So I'll say remove set, which is the set that you need to remove, is going to be if the bit counts at this pindex is now equal to 2, then we need to somehow remove this bit. Remove set dot add this the index that this is found. Interesting. Maybe I can do a hash for this. Maybe I can do a hash for this. Because I'd have to. I'll do the hash and maybe do a hash in a bit. So you added in the right to your bit count. So now, while left is less than right, and while left is less than right, actually, while remove set, the length of remove set isn't 0. So while there's some bits that we need to remove, then we're going to do left is equal to or left value, left number is equal to num set left, and then we have to do the same calculation here. This is why this seems very inefficient. You have to do like 32 operations per number. So the pindex, the power at this pindex, and then the bit value is going to be the power versus the left number, and then you decrement it, and then if the bit counts at this index is now 0, then remove set dot I think it's discard rather than remove. I think discard is the one where it removes it if it's present, but it doesn't give it error if it's not. Yeah, discard. Because technically it could be the only one of that, but we want to go for the one that's duplicate. No, actually, this is not correct. It could go back down to 1. It doesn't have to go down to 0. So if the if the bit counts of this index goes down to 1, where it was previously 2, then discard it. I guess the other way of doing this would be like if bit counts of this index is equal to 2, then we know then this has to be something that we need to remove. Set dot remove this index, and then lower the bit count at that. Wow, that's really bad syntax. And then that loops until it finishes closing the window, and then back to that. Left should increment for sure. The size of the window is right minus left plus 1. Okay, let's see how slow this is. Let's see when that's right. 3. Okay. Well, it's not giving total crashing, so the right numbers, nums at right. You have a remove set. Let me go ahead and after you add in the right number, just print out what the bit counts are and what the remove set is. Ah, shucks. This is I think I might have screwed up this. This should not be a bitwise and. Should it be bitwise and? No, it should be, right? There's too many things that are not 0 in this case. Powers should be powers of 2, right? Okay, yeah. And then if you do a bitwise and between any power of 2 and the number 1, it should be 0. Oh, I think I wanted to do bitwise. Why is this? So what I'm expecting here is if you do bitwise and between like 1 and 1, it should be 1, but then if it does a bitwise and between 2 and 1, it should be 0. But here it's actually 3. 2 and 1 should be, unless I'm using the wrong operator. I'm using the wrong operator. I'm using maybe, no. Oh my god, I'm using bitwise exclusive OR now. Oh shit. Alright, this should be bitwise and. Okay. I don't think bitwise exclusive ORs is used in this instance. Okay, that's better. So it's the first time it goes through, it's 1. And let's just print out what the answer is for each loop. Okay, so after the first loop it's 1 because that should be fine. And then the second loop through extended out the window to 3. And 3 should have overlapped with 1, so there should be something that it needs to remove. So it needs to remove why is there 2 something that needs to remove? I think it should only need to remove 1, and that was the bit at index 0. But also saying that it needs to remove the bit index 1. This seems wrong. Oh well, the bit counts is actually wrong as well. If you're at 1 and 3, then there's 2 bits at 1 and 1 bit at 2. So that cannot be right. Bitwise value and then the right number. Right number is increasing each time. Bit count at this index. If the bit counts at this index is equal to 2, 3 is 1, 1. 3 is 1, 1 bits. So the bit counts. So this is wrong. You're adding the bit value. Unless the bit value is actually like the bit value should be for the powers of 2. Alright, let's do a test case here. 2 and 3. Oh. I think I just need to have this thing equal to whether or not this equals 0 or equals 1. Is there... So yeah, I was just hoping to have this thing be equal to 1 or 0. Okay, I think maybe I'm just doing bitwise operations inefficiently here. Yeah, I'm doing this inefficiently. I think the correct way of doing this is actually to just do the bitwise AND with the last bit and then remove that bit from the number. Okay, so every index image 32, that's fine. I think I need to get rid of this powers deal. Do a bitwise AND of the number n1. Bitwise AND with the number n1. So that's the bit value of the leftmost bit or the rightmost bit within that right number. It increases whatever this index is, and then if it's 2, then add it, and then afterwards you need to make the right number shift, remove the right number's rightmost digit, and I think that's it's that. Rightmost shift by 1. Okay. I think it's that. And then same thing here, just remove the powers bitwise. So it's just the left number and 1, and then shift it to the right. Okay, let's see if that is correct. I think is it? I need to be left shift and equals, I think. It's shift and reassignment. Okay, there we go. I don't need all these printouts. Alright. See how slow this is. Wrong answer. Okay. Okay, so am I going to be able to tell, based on this results, what is the issue? So my answer was 13, the correct answer was 8. Alright, I think I should go back to printing these, I guess. Okay, so first number, those are the bits for that number. There's nothing to remove. Second, those are the overlapping bits. And the answer is still 1 because it probably closed it down to that. I'm going to just say what the left and right number indices are. Okay, yeah, so after the first iteration, left and right indices are at 0, 0, 1, 1, 2, 2 because there's some overlap, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10, 11, 11, 12, 12, 13, 13, 14, 14. Okay, now this is when it actually doesn't start overlapping. 14, 15, 16, 17, 18, 19, 20, 21, 22. There's overlaps in those bits. So it closed the rightmost or the leftmost number by 1 in the window. Opened up the window by 1, closed it back by 1. Right, so it looked okay-ish, but the expected one was 8. Okay, so I said 13 based on the fact that the biggest window that it saw was what? 14, 20 is 6, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7. 8, 9, 10, 11, 12. Well, 13. Okay, so somehow it didn't get the last stuff correct. So the ending of this thing is incorrect somehow. So how did it get wrong? Wait. Why are these bit counts so high? Like, they should never go up to 3. Should never go up to 3. They should only go up to 2. And then it should go down back to 1 when you remove it, I think. Unless I'm keeping track of my indices wrong again. So the index is the number of times you removed it. Or the index is the number of times within the loop, so I think that's consistent. While the remove set doesn't equal 0. So here you increased it. Okay, so it's this one. So it went from all zeros and ones here to somehow after the removal, somehow, so all zeros and ones here, and then there's some 2's here. There should never be a 3. Unless I'm not removing enough. So I remove on the left, and then the bit count, if the bit counts prior to my removal is 2. Oh shit. Okay. Prior to my removal is 2, but also I am removing this thing, and also I'm removing this thing. Wow, that's a really bad mistake. What's the thing here? If the current index is something that I want to remove, and the bit value is 1. Okay, yeah, so if the bit value is 1, and this index is something I want to remove, then I remove it. Okay. Okay. Alright, no more prints. Huh. It's gonna be pretty slow. Yeah, seems like it'd be pretty slow. Okay, so how to improve this? So what if I kept for each what if I kept a hash, a dictionary for each index, and what if I kept a dictionary for each index? And the dictionary would be to see the index of the number that has that on. So what if I, like, the indices are 0, 1, 2, 3 here, and let's say let's say I had originally a number that was 0110. So at index 0, there would be nothing for the dictionary. At index 1, it would have 0 as a number that has that bit on. At index 2, or in the dictionary for 2, there would also be number index 0, and there'd be nothing for 3. And then when I do the second number, the dictionary at index 0 would have 1 as a possible number that has that and doesn't change anything else. And then for this one, it would now place this thing here. It would place 2 here, and it would note that 1. It would note that 1, the index 0 no longer applies. So at any index, there has to be a unique value, and there can only be one value at the index. And then I keep track of the earliest or the latest one as I go through this. Keep track of the leftmost window, and if the left side is bumped up, then it needs to be bumped up. Okay, let's just try this. I think this is as far as this solution is going to go. I don't think this is going to get optimized. So let's try not having a bit counts, but a bit dictionary. And let's say this is a default dictionary of int. And for every right number, I don't know if I need this remove set. I'm going to say probably not. For every of ints, I think it's going to be a default dictionary of lambda x, where lambda x is -1. I think that's the, let me just double check here. Let's say bit dictionary of 0 is equal to 5. I'm just plus equals 34. I'm just making sure that oh shoot. Print lambda x default see default dictionary -1. For this. Oh. And then oh, it's just lambda -1. All right, just making sure that works. Zero is 3. Okay, that's fine. Okay, so you have all your bits. So the default dictionary for a particular index, I guess you don't actually need a dictionary. You can just say that it's going to be an array. I guess how is it different than the counts, actually? So instead of storing a count, you're storing the place. So let's say it's -1 times 32. So what you're actually storing here is this index. So if the bit value is equal to 0, I know that I don't need to worry about this thing at all. I do need to shift over the number, but otherwise there's no way that this is going to affect anything. Now if it doesn't equal 0, then what's going to happen? Then the left side needs to remove this number. The left side needs to remove this number. So if this number is past where the current left is, then bit counts at this index. So bit counts, or no, sorry, this is now bit array. Bit array at this bit value stores, bit array at this index stores where's the last time you saw something at this spot, and you cannot use that spot anymore. So you need to do that spot plus 1, whatever is after it. Yeah. And now you say that the bit array for this index is equal to the current spot, because this is now the last time you saw it. I don't think you need to have a set anymore. Okay. Do you need to actually do stuff on the left window? Not really, because all you're doing is just keeping track of the latest spot, the latest left. And you never really increment left besides using this thing. Okay, so size is equal to right minus left plus 1 now. Okay, let's see if that works. Boy, that definitely did not work correctly. Okay, so let's go ahead and just print after the loop, print what our bit array is. I think. Okay. So the first time through the loop, 1 is the number, and so the bit array states that the last time you saw something at index 0 was at index 0 with the nums. A 0 index bit is 0 index in nums. Your answer is 1, sure. Okay. The second time through the loop, the right number is 3. Our bit array, the last time you saw something has a bit value of 1 in the 0 spot is this index, 1. And 1 in the second spot is also 1. The answer here should be 1. Our left should be 1. But our left is not 1, it is... Oh, this is max, not min. Okay, there we go. Wow, very slow. Okay, okay. How to improve then? So, for each right number, you see the bits on the right side. If that bit is 0, then just move on. Otherwise, you do the left side and then you update that bit. So the number of operations that you do on any given so pretty much this is, I can't actually do 32 operations per number. So it has to be something more efficient than this. Cannot do 32 operations per number. So what if you for any given number on the right side of your window, can you just do some sort of exclusive OR rather than AND? Exclusive OR. Exclusive OR. Then what would happen is, so for exclusive OR logic, so 1 and 0 is going to be, well, and logic, most people will know, but 1 XOR 0 is going to be 1, 0 XOR 0 is 0, and 1 XOR 0, or 1 XOR 1 is 1. No, sorry, 1 XOR 0. 1 XOR 1 is 0. Exclusive OR is like, are these two not the same? If you do exclusive OR with all the numbers in your subarray, then you should end up with something that is, if you have an exclusive OR with everything in your subarray, you have basically a summation of all your values, of all the bits. It should basically get bigger, and if it doesn't get bigger, then you know that there is something that is making it that's a conflict. So, interesting. So what if you did a subarray like some value using exclusive OR? When you see a right number, you do it on that you do exclusive OR with that sum value. If it's bigger than then you know that that's good. That's not right. That's not right. It could be going lower in some spots, but bigger in other spots. Could be going lower in some spots and bigger in other spots. Feels like you have to do something that looks like pretty darn efficient. Exclusive OR over all your window, where add bits of number at the right index. How do you track that? So 1, 3. If you do exclusive OR on that, you get you get 2. I guess the ones place cancels. And you know that there's some overlap. And then 3 and 8. If you do exclusive OR, if you do the exclusive OR between two numbers bitwise, and the value that you get is equal to the sum, the exact sum, then you know that there's no conflicts. But if it doesn't equal the exact sum, then you know that there are conflicts. And how do you detect where the earliest conflict is? You detect the earliest conflict when you do the exclusive OR on the right side. But there might be multiple conflicts. So you might have multiple conflicts. So if there are multiple conflicts, then you just can't go backwards, right? Like you just can't go from right side to the farthest left. It just doesn't make sense. That would definitely be like n squared. Because you might need to go back a huge number of numbers. So you do exclusive OR to extend it out, see if it's the exact sum, and then can you do exclusive OR on the left side? And while the left side overlaps with the sum, oh yeah, while the left side overlaps with the sum, then you while the left side overlaps with the sum, oh, huh. What if you did what if you did an exclusive OR over everything? Okay, I know how fast this thing is. I think this is as far as it's going to go. I think maybe if you did a prefix exclusive OR, prefix XOR. I'm not sure if this makes theoretical sense, but let's say you have your prefix array start with 0, and for every number I think you just see value in the range in your numbers. You're going to do prefix or dot append that value exclusive for with the last value. I think so. Exclusive or so the thing with exclusive for is if you have multiple of a number, they cancel out. Multiple of a particular bit cancel out. And so how would this work in this instance? Let's just print out the prefix exclusive OR for this array. So 0 is 0, so 0 is 0, 1 is 1. If you do the exclusive OR of the first 2, then it's going to be 2. Exclusive OR of the first 3, it's going to be 10. Exclusive OR of the first 4, it's going to be 58. And the first 5, it's going to be 48. So at any given point on your right side, you want to for any given point on the right side, you want to see what do you want to see? Oh gosh. 58 is what you get if you had 1, 3, 8, and 48 all exclusive ORed. And 10 going to 58, where 10 exclusive ORed with 48 becomes 58. You know that there's no overlap there, so you know that that's good. And then 58 exclusive ORed with 10, that went down to 48. You know that there was some overlap. The question was, how far back was the overlap? It's not like you can just say so the overlap from 58 to 48, there was some number of bits. There had to be an 8 and a 2. And so the question is where the 8 and the 2 bits were found. They were found at the 10. Okay, so the left, okay. Our window is 1, 1 after the first one. Our window is, or 0, 0 is after the first one, 1, 1 after the second one, 1, 2 after the third one, 1, 3 after the fourth one. And then, so it's 1, 3, 1, 3. Because it's, yeah, 1 to 3. How does that even add up to 58? No, that should add to 59, right? But we had somehow canceled this thing. So our summation is, so our window should have been 48. No, our window should have been 10. The 3, no, our window should have been, the exclusive OR of our window should be 3 and 8, so it should be 11 at this point. 11. So let's 1, 1. When we see that we exclusive OR the 1 and the 3 and we get something smaller, we get 2. Then we need to get rid of duplicate 1. So we do that until we get back to a 3 here. So our window is currently 3. How do we know that getting rid of just the 1 was adequate? Okay, our window is 3, exclusive OR 3 and 8, and we get 11. So that should be fine. We exclusive OR 11 and 48, and we get 59. That should be fine. Exclusive OR 59, 10, and get 49. Huh. If while the exclusive OR of our current window and the right side and the left side number doesn't add up to the sum, then we need to remove the left. Is that correct? No, that's just not correct, right? Because we detect that there's some overlap. The overlap doesn't necessarily occur right at where the left is. So the exclusive OR between this number and this number, the 1 and the 3, which is 1. 1 needs to be removed. And while there's still stuff to remove, then you take it from the left side. Well, there's still stuff to remove. You take it from the left side. But you take it from the left side. Do you know when you've taken enough from the left side? So you take it from the left side until you see a 1. Here, exclusive OR, there's a 1 that you need to remove. So you take it from the left side, then you have a 3 left over. You have 3 left over. And then you add in a right side number. That's fine. And then you add another right side number. That's also fine. And then you add in this number, and that reduces it by exactly 10. So you need to somehow remove 10. Start by removing the 3. That gets you to remove the 2 out of the 10. But you're not subtracting 3 exactly. You're subtracting the bits of 3, where the bits of 10 are 8 at the 8 spot and the 2 spot. So the 8 spot and the 2 spot, the bitwise AND of those things is 2. So you're removing 2 from 10, and that's not enough. So then you keep on doing it until you have something that is enough. Bitwise AND. Okay. Okay, I don't think you need this prefix XOR. I don't think you need the prefix XOR. I'll just keep it for now. This then all go away. So for every right number in your range, or right index, the right number is going to be, let's say the current XOR is going to be 0. Right number is the number at the right side, which is the nums at the right. And then the difference, you have to find the difference, right? So current XOR, the difference should be, let's say next XOR is equal to the current XOR exclusive OR with our right number, and the difference, so if the next XOR not equal to the right number plus the right number plus the current XOR. So if it's not exactly non-overlapping, then the sum is not going to be equal to it. So that means we're going to calculate the difference. So we're going to calculate how much of an overlap there is. So difference is going to be next XOR minus current XOR. And then we're going to remove it while there is a difference. While difference not equal to 0, then we'll go back to having a left index here. Left number is equal to the nums at left. And if this left number at all agrees with diff, so the overlap is going to be diff and left number bitwise, and difference is going to be subtracted by the overlap. All right, okay. 5s all around. Okay, interesting. So let's go ahead and print out the, oh, whoops, I need to update the next XOR to be the current XOR, or the current XOR to be the next XOR, whatever. While difference less than equal to 0, not equal to 0. Next out of range, think and left less than right. I'm not sure why I would need this. Shouldn't. I feel like I should need that. Okay. At least it didn't crash. Somehow did the first one correct. I need to do this within the while loop. Current XOR equals next XOR. So you remove it. While you remove it, you should be updating your current XOR now. So you get the left number, and then you move the left number. So yeah, current XOR, exclusive OR, exclusive OR with the left number. I don't think you need that. Alright, went back to losing everything. Okay. So let's see. Let's go ahead and print the current XOR and the next, what the current number is, the current XOR and the next XOR. Alright, so the first one, it's 1. Great. Second one is 3. And let's see, print overlap detected, removing stuff. I should have detected an overlap here. Next XOR, the current XOR is 1. The next XOR, oh, say, hit the right number, which is 3, plus the current XOR, which is 1. Does not equal to the next XOR. So why doesn't it detect it? The next XOR is 3. Oh, the current XOR is 0. That's not right. It's removing everything. Okay, well, if the next XOR, so 0 and 1, it's not doing that correctly. So 0, next XOR is 1, size is 1, left is currently 0. Left is currently 0. Current XOR for the first time through. Maybe I should just start with 1. So current XOR is equal to the first number, which is nums at 0. Go from range of 1 to the n. Okay, let's try that. I should say left starts with. Okay. So it's removing some stuff. So 1 XOR with 3 is not 4, so there's overlap detected. And then let me say print left, right answer. So left is now right, or left is 1, right is 1. Answer should be 1. Right minus left plus 1. And why the answer is 0 at that point. Actually, why is the say left? Why would the answer be 0? That doesn't make sense. It's right minus left, 1 minus 1 plus 1 is your size. Your answer is the maximum of your. Oh, my answer. No. My answer. How odd. Right is. Oh, wait. My left side is 0. My left side is 0. My right side starts at 1. There was right minus left plus 1. 1 minus 1 plus 1. Oh, I'm printing out this. This is the wrong spot to print out that. Alright, my answer should probably start with 1 anyways. My left side should start at 0. Okay. So, yeah, it's still 1 off. Answer is 1. Next one, 8, no overlap detected. Next one, 48, no overlap detected. Next one, 10. My current XOR is not correct. What's going on here? Current XOR is not correct. Next XOR is current XOR. Oh. Yeah, this is not. Next XOR equals current XOR minus rnum. And let's say diff equals next XOR minus current XOR. And I'll say current XOR is equal to, at this point, I should be not really worrying about next XOR. And then I wonder if the difference could be, difference can be negative as well. The difference can be negative. Absolute value of this. While if the difference is not if when do I need to update this? If I update this right now, I can't use it in the if statement. So I do next XOR is the current XOR and the right num. If the next XOR doesn't equal that, I think here it should be right there, and then I guess I could just use the difference right here. If the difference does not equal right num, and then I just can have this thing right here. Okay. Next XOR difference calculation. Just reset the XORs, current XOR. Do this. While I do this, it changes the current XOR. Okay. Okay, still incorrect. So 1, 1. Second one is 8, 11. That doesn't seem right. That should be... No, I guess that is right. Okay. The current number is 8. The XOR is going to be 11. That's totally fine. Next one's 48. XOR is 59. That's totally fine. So the current answer is 3. Yeah. So I shouldn't be taking the absolute value here. If the difference is exactly if the difference, see, this is as long as the next XOR is smaller than the current XOR. Yeah. As long as the next XOR is bigger than the current XOR is the issue. So let's try this logic one more time. If next XOR, no, the difference has to be exactly the same and positive. Has to be exactly the same positive. It just cannot be just bigger because some stuff can be overlapping, but on a smaller place value than something that's non-overlapping and a bigger place value. So if the difference, so it's not the absolute value. What should it be then? Yeah, so it should be next XOR subtracted by the current XOR. And if that number is not exactly equal to the right number, then what do I need to get rid of? I need to get rid of the spots that are overlapping. Spots that are overlapping would be where the spots that are overlapping would be where I need to get rid of this right now. Where there's overlap between the current number and the right number and the why don't I just do differences in the why don't I just do differences in the current XOR and the current number? And? No, it's not an and, is it? It has to be a 1 there and a 1 there. Yeah, that is the difference. That difference is not 0. That difference isn't exactly 0. Then you need to, actually I guess it's not if it is, then while it is. And left is less than right. Okay. Difference is, actually I guess I don't really need to worry about next XOR anymore. So it's just difference is the current XOR and the right number. And then I need to update the current XOR to include the right number. Exclusive OR with the right number. And then while the difference is not 0, we're going to take the left number. If there is any overlap between that number and the difference, then we're going to subtract that overlap, move that number from the current XOR. Alrighty, okay. Get rid of this print. This print. I'm not using prefix XOR. Oh, okay, well, that sure beats the previous solution. Okay, so how to optimize this? You have your difference calculation. You have your current XOR calculation. while there is a difference, you're going to determine the overlap. I guess there's a bunch of things here that you could probably just shortcut here. Just combine current XORs is that. Just gonna get rid of the overlap thing here. Difference and the left number. And I can just say the left number is nums at left. Okay. Size, I can just say that's right minus left plus 1. Okay. Well, difference not equal to 0. Guess I can also do just right number as nums at right here. Oh, baby. Above 50%. That's above average. That seems fine. That seems fine. Is there a shortcut to doing some of this stuff? Like, is there some sort of optimization that speeds this up? What is the runtime of this? 94 milliseconds compared to 100 milliseconds? Yes, that's pretty darn close. Take the right side. Take the right side. Take the difference. Yeah, I don't know. I mean, this is a very condensed set of solutions. It's not like you can actually optimize all that much here, I don't think. Alright, I'm just going to go through the summary of how this works. Tidy it up here. Okay, so to summarize, how did the solution go? So this is still a sliding window technique. You open window on the right and detect how much detect where the right number conflicts / overlaps with the current nice window using bitwise and. So okay, so track Windows bits using exclusive OR. Have a XOR kind of sum value. So when you do exclusive OR on kind of non-overlapping values, or bits that are 0 and 1, then it becomes 1. And if you do exclusive OR on bits that are 1 and 1, it becomes 0. So if your wait, do I need exclusive OR here? Can I use just OR? I guess I could use OR on the first step here. Guess I could use OR on the first step here, but not on this step. Okay. So the XOR is basically like a sum value, where if you exclusive OR with a previous value, let's see, I'll just read this here. Tracks window bits using XOR, have an XOR for the sum value. Open the window, detect where the right number conflicts or overlaps with the current nice window using bitwise AND. Yeah, so if, for instance, our numbers were 0 in bits, 1 is 1, 3 is 1, 1, 8 is 1, 0, 0, 1, 0, 1, 0. 3 is 1, 1. 8 is 10 and 2. 8 is just 1, 0, 0, 0. And then 48 is 1, 1, 0, 0, 0. So 1, 1, 0, 0, 0. 32, 16, 8, 4, 2, 1. Okay. So if we did a bitwise XOR of our window here, after the first one is just 0, then 1, the XOR here is going to be 1, 0, because one exclusive OR with 1, 1, this 1 and this 1 cancels to become 0, and then the 0 in front of the 1 is not going to cancel anything. So detect there's a difference. In this case, the difference is there's an overlap of 1. Like if you do bitwise AND between those numbers, the overlap's 1. Then you need to remove stuff in your left side by that, so until you remove the difference. Remove left side numbers until difference is numbers detecting overlap till difference is 0. So while there is some overlap, in this case there's 1, we see what the overlap is by using what the left side number is and the difference that we want, the bitwise AND of that. Subtract that from difference. Remove the left side number from our current XOR sum, and then increment the index of the left. And then do that a bunch of times until you get to something where the difference is 0, which means you removed all the overlap from the original new number and the current sum. I'm pretty sure this could be an OR right here. I'm pretty sure. Logically, XOR and this. No, that's not right. This has to be an AND, or it's this OR, because we want to yeah, we need to keep track of the exclusivity. Yeah. Alright, time complexity for this should be just O of n. For each number, you're going through it once. For each index in the array, you're going through it once. The right increments once. The left can only increment as much as the right, so it's going to increment once each time, or on average once at most. And then space complexity is, or time complexity O of n. Right index goes through each in n size array. Left is less than left increments at most right times. And there's no extra, there's a constant amount of work each loop. And then space complexity, we use a bunch of variables that have constant size. There's no other arrays, so this is O of 1. Alright, I did make a comment that I didn't think this was Xcore using, but I guess I was wrong about that. Yeah. Good refresher.